Okay, so we are now going to be talking about the matched pairs t-test and t-interval. In this case, in the two-sample hypothesis test of the mean, we're interested in determining if the mean of one population is equal to the mean of another population. In the unequal and the equal variances two-sample t procedures, we were looking at the difference of means. So the difference of means. Now we're interested in looking at the mean of the differences. It's a subtle but important difference. So what happens is we're calculating the differences between the two groups and then doing the hypothesis test. So sometimes we want to compare treatments or conditions at the individual level. The data sets produced this way are not independent, they're paired. And so when that happens, the individuals in one sample are related to those in the other sample. An example might be pre-test and post-test studies that look at data collected on the same sample elements before and after some experiment is performed. Twin studies often try to sort out the influence of genetic factors by comparing a variable between sets of twins. Using people matched for age, sex, education levels, and a social study allows us to cancel out the effects of these potential lurking variables. And so in these cases, we use the paired data to test the population mean of the differences. We lose degrees of freedom, but we get rid of lurking and confounding variables by using paired data. And I forgot to write this above, but when we are interested in the difference of means is mu1 minus mu2. The mean of the differences is mu of the differences is equal to 0. So that's the difference there. So let's go ahead and do our first example. So we're going to do the paired t-test. A psychologist has randomly chosen 5 people to be tested before and after some traumatic stimulus. Researchers believe that response time increases after exposure to the stimulus. It's known that the response times to stimuli are normally distributed, so we're also told normal. In paired inference, we're interested in if the differences between the pairs of data. And so we have subjects one, two, three, four, and five. Their before response, their after response, and the differences. And so the differences are what we're interested in. We do our test or our confidence interval on the differences. This confidence interval or hypothesis test reduces to a one sample t-test or t-interval. So once we calculate the differences, it's just a one sample test or a one sample interval. So to develop the hypothesis test, we still need our hypotheses, our conditions, and our sampling distribution. The paired t hypotheses are that the mean of the difference is equal to 0. The mean of the difference is greater than 0 is the alternative, less than 0 or not equal to 0, but you must state which direction you subtract your data to get the differences. Differences, whoops, DIFF, of A minus B is not equal to the differences of B minus A. So order doesn't matter when you're doing the not equal to test, but it does matter when it's greater than or less than. So just always get in the habit of writing down which way you've subtracted and using the same direction you write your hypotheses in. So the conditions are that we have random samples. Both samples are random, just random sampling like we normally have. Normality can be met in one way or another. The differences are normal because you're told so. D bar, the average of the sample differences, is normal because you have large samples, and that means that the number of differences or pairs is greater than or equal to 30. That's the central limit theorem working. Or the graph of the differences is bounded and symmetric. And then the data here are paired instead of independent. So they are dependent or paired. The test statistic is a t-test statistic where we have calculated the average of the differences, d bar, minus 0. So we're almost always saying that this is 0, divided by the standard error of the differences. That's just the standard deviation of the differences divided by the square root of n, where n is the number of pairs. So this is important. We are talking about the number of pairs all the way through this test. So this whole test is just a one sample t-test. Conceptually, the paired t-test is just like a test for one population mean, except in testing our sample, we're testing the set of differences between two samples. For our example, our data simply reduces to the sample of differences. The variable studied becomes x bar of the differences, or d bar. Some books use x bar sub diff or d bar. You can use either one, which is the average difference between the pairs. So what statistics am I going to need? I'm going to need all of my differences. These are my d sub i's. I'm going to need the average difference, which is d bar. I'm going to need the standard deviation of the differences, which is s sub d. And then I'm going to need n, which is the number of pairs. So again, be careful, it's the number of pairs. And then what graphs will I need? I'll need a graph of the differences, which is a histogram, a QQ plot, or a box plot of the differences. And so we have numerical data here. It's paired numerical data. Let's look at an example. So a psychologist has randomly chosen 5 people to be tested before and after traumatic stimulus. Researchers believe that response time increases after exposure to the stimulus. It's known that the response times to stimuli are normally distributed. Test that the response time is greater after the stimulus at the alpha equals 0.10 level. The data is found in the trauma Excel file. The R code is also included, and I'm going to pop that open in just a minute. We need our differences. And so the null hypothesis is that the mean of the differences is equal to 0. And the alternative hypothesis is that the mean of the differences is either greater or less than 0, depending on which way you subtract. So I'm going to say D is equal to, we want that after is bigger than before. So we want after minus before should be greater than 0. So mu sub d is greater than 0, where my differences are after minus before. By the way, I'm subtracting the opposite way we had it from up here. So I'm doing it the way that I want based on what we were asked to test. You must include this statement when you write your hypotheses. All right, so we want the statistics where D is after minus before. So we want X bar sub D. We want the number of pairs, and we want the standard deviation of the differences. And number of pairs is obviously 5. We can get that ourselves, but we can get this out of R as well. We're going to want a graph of our differences. And in this case, we could do a histogram or a box and whisker plot, but we have a really small set of differences, so we're probably going to want a QQ plot. And then my conditions that I'm going to want to meet are random sampling, normal, and then paired data. Well, random sampling, almost certainly not, because they're using people who've been exposed to trauma. And so people who've been exposed to trauma is a convenient sample. You can't expose people to trauma. That would be unethical. And normality, we are told that we have normal data, but we're also going to look at our QQ plot. That one's going to be pretty normal as well. We'll just look at it in a minute. And then we have paired data. All right, so when we have this situation, we can do a paired t-test or t-interval. And let's go ahead and look at R and get some of the stuff out of it. So I've already imported the trauma data, and for the trauma data, I have the before data, the after data, and the subject number. And subject number really is categorical, although it looks like a number to R. And so the first thing I'm going to need to do is actually calculate my differences. So my differences are going to be the afters minus the befores. So differences equals trauma $after minus trauma $before. I'm going to run that code and my differences show up here on the right. If I want to take a look at this data again, notice that those differences do not show up in my data. But because they're in my environment over here on the right, the differences do exist, and I have subtracted the correct way. I want to quick take a look at a box and whisker plot of my data. There's my data for the differences, and the differences range from -5 up to about 15. I'm going to look at the QQ plot and the histogram as well. There's my histogram. You know, for a set of data that only has 5 points, that's pretty normal. But remember, histograms are not something we should be using with a data set that's this small. So instead, I'm going to do the QQ normal plot of the differences, and I'm going to put the line in there as well. When I look at this data is relatively normal. All of these points are following this line, so that's very nice. The other thing that I'm going to do is calculate the mean, the standard deviation, and the sample size of my differences. So mean of the differences, standard deviation of the differences, and length of the differences gives me all of the statistics I need. The mean difference is 4.6. There are 5 pairs of data, and my standard deviation is 9.17. So I can write all of these things down. X bar of the differences is 4.6. Sample size is 5. Remember, it's the number of pairs. Standard deviation is 9.17. My QQ plot looked something like this. It was pretty nice. And then you can look at your box and whisker plot or your histogram if you want to, but this is such a small data set, I'm not going to. And then I'm going to go ahead and do the paired t-test in R. And so when I do this paired t-test in R, we're still using the exact same commands we were using in the last 2 tests. So we're doing a t-test on the after and the before data, that the mean difference is 0, but this time, instead of paired equals false, we use paired equals true. And because of that, we don't have to say var.equal is true or false. And all of those notes are up here. And then your alternative is greater. And if we were doing a confidence interval, we would do confidence.level is equal to 0.95 or whatever we wanted. And I have my paired t-test with a t-test statistic of 1.12 and a p-value of 0.1625. And by the way, the mean difference, this is the sample mean difference d bar that shows up in this output. Okay, so p-value is 0.1625, t-score is 1.12. So t equals 1.12, p-value equals 0.1625. So we make our decision the same way we always do. My p-value I compare to alpha, 0.1625. Compared to any alpha, doesn't matter. We were told to use 0.10. It's bigger than that, so we fail to reject Ho. So our conclusion, there is not evidence. You could include your alpha level or your p-value. There is not evidence at the alpha equals 0.10 level to show response time is greater after trauma. And what that really means is there's no evidence that mu sub d is greater than 0 when d equals after minus before. So you do have to include that subtraction statement there. The paired t confidence interval is exactly what you'd expect it to be. It's d bar plus or minus t times the standard deviation over the square root of n. And what we're estimating here is mu sub d. It's the mean of the differences, where d bar is the average of the differences, s sub d is standard deviation of the differences, and n is the number of pairs. The T procedures for paired data are exactly correct when the population is exactly normal, which is rare. The T procedures, though, are robust to deviations from normality, but the sample must be a random sample from the population, and outliers and skewness strongly influence the mean, and therefore the T procedures. Their impact diminishes as sample size gets bigger, though, because of the central limit theorem. The confidence interval here has the exact same conditions as the hypothesis test, so you should be able to do both of these now. All right, that's it.